Welcome back, students. Let us now go over to section 1 of this notebook, homogeneous and non-homogeneous equations. And let's begin with some theoretical background, the fundamental theorem of linear ordinary differential equation. Let's suppose that we have a linear ordinary differential equations defined in a certain open interval I, and inside this I we have to have a starting point t0 with appropriate initial conditions. In that case, there has to be a solution. Not only that, there has to be one and only one solution in a certain subinterval j of I. For example, this I is negative infinity to positive infinity and t0 is say 1, and this j will be a subinterval, say for example 0 to infinity. It doesn't have to be equal to I. But in any case, that's not really the focal point here. The real focal point is the uniqueness. Why? Because the uniqueness tells us that it does not matter which method you find to find a solution. You may even guess. But if you find one, then that is the solution. Well, here's an analogy. Let's, for example, lower level students are doing something like this. X squared minus 3x plus 2 is equal to 0. Okay, all right. And solve this equation. How do you do that? X minus 1, x minus 2 is equal to 0. Therefore, setting each factor equal to 0, then we have x minus 1 is equal to 0, or x minus 2 is equal to 0. Therefore, x is equal to 1 or x is equal to 2. And this is a typical solution, and you don't really need existence theorem or uniqueness theorem here because this came from continuous flow of logic. Well, there was one hard part here. From here, right inside is 0, setting each factor equal to 0, there was some difficult algebraic structure came into play here, integral domain, but otherwise nothing too fancy. Let's suppose a student didn't know any of those, but just guessed. Try x equals to 0, it doesn't work. Try x equals to 1, force it in, it works. X equals to 2, force it in, it works. X equals to 3, it doesn't work. X equals to 4, try it, it doesn't work. X equals to 5, try it, it doesn't work. And then give up here, and then these two work, so these got to be a solution, or excuse me, these two. I'm gonna give the student full credit, even though the student found out the answer. Well, if this is something people do in college algebra class, then that would be problematic because the student tested only 6 numbers out of infinitely many possible, not even discrete. And the student happened to hit both of the solutions, but this solution method is terrible. In differential equations, on the other hand, this kind of thing is perfectly acceptable because of this, the fundamental theorem. We have the uniqueness, so even if we guess, even if you do something whatever wild, if we find one solution and that is the solution, that's it. And we're going to deal with a lot of different methods here, and none of these methods is perfect, as a matter of fact. Sometimes it works, but more often than not, they fail. But we still try, and then if we had a solution, and that's it, that is the solution. Why? Because of this fundamental theorem. No matter what method you use, if you're lucky enough to hit the solution, that is the solution. That's why we are doing that. And the proof of this fundamental theorem and things like that, oh well, I used to cover this in real analysis too, but not in differential equations, not even differential equation 2. So let's not bother, but just remember why we are dealing with this fundamental theorem here. Okay, next let's go over to homogeneous and non-homogeneous equation. This kind of thing is called homogeneous equation, equal to 0. And this kind of thing is called non-homogeneous equation, equals to something else, some f of t. Simple? All right. Now, why is homogeneous equation and non-homogeneous equation? Why is this classification so important? Especially, why is homogeneous equation so important? Well, that's answered in the next subsection here. Particular solution. Let's suppose there's one solution, particular solution, which came out of nowhere. It may have been given, or you may have been just lucky enough to guess. Let's suppose that we have a solution. Then, any solution, general solution, can be written as a solution of homogeneous equation plus that particular solution. And that's why h of t is a solution of this homogeneous equation. In this particular solution, there's only one solution, and this one may include some integral constants because you see, as you saw before, if you take the antiderivative, c pops out. If you take two antiderivatives, we have c1 and c2. If you take the three antiderivatives, and c1, c2, and c3 pop out, and so on and so forth. And this one may have some integral constants in there. And if you use common sense, we're talking about the nth derivative. So this will have n integral constants, c1, c2, c3 of the order of the cn. And this is very general, and this is just one solution. So if you find something general about this homogeneous part, then you can solve anything, as a matter of fact. That's why homogeneous is so important. By the way, here's a proof. Let's suppose y is any solution, and then define yh of t as that y of t, which we started off with, minus yp particular solution. Define it like this, okay? And let's do the color coding, blue, and then this is red. Then this y minus yp, which just named it as yh, is a solution of this homogeneous equation, which is not difficult to prove because if you just put it into this left-hand side of that differential equation and then just apply the derivative nth times, the same as the difference of the derivative. Derivative of the difference of the derivative, and so on. And then if we apply algebra, all the y part minus all the yp parts. This one is equal to f because we assumed it's a solution. And this one is also equal to f because it's a particular solution we started off with. So what do you get? F minus f is equal to 0. Conclusion, yh is a solution of homogeneous equation. And if you do a bit of an algebra, flip it over, y is yh plus yp. And the general solution of non-homogeneous equation has this kind of form. This is something you just guess or get this homogeneous first and then derive from there. There are some ways to get this particular solution. But this one has all the arbitrary constants in there. This one is real general thing. And that's where the primary focus of our attention will be. The solution of homogeneous equation. Let's see, shall we do an example here? This is not going to be too difficult an example. Let's see, y1, y2, and yp be functions defined as follows. Okay, we just defined them. Cosine of t over t, sine of t over t, and y of p, yp, particular solution as sine of t. And then prove that y1 and y2 are the solutions of this homogeneous equation. How do you prove that? If you had to solve this equation at this and get cosine of t over t and sine of t, it's going to be really hard. But if those are given and verified, that's not too difficult. All you have to do is to take the derivative, second derivative, plug those in and see if those turn out to be 0. Not difficult, but tedious. As a matter of fact, it was so tedious that I just used Mathematica to do that. Let's see. T times the second derivative, 2 times the first derivative, t times the original function. Simplify that, we get 0. How about sine of t? The same thing. T times the second derivative, 2 times the derivative, and then t times the original. Simplify that, we get 0. And finally, for sine of t, t times the second derivative, 2 times the first derivative, t times the original, and simplify that, we get 2 cosine of t. Just as expected. Oh, excuse me, what am I talking about here? This was not really necessary here. Part A of this problem was only asking about homogeneous, so only these two would have been necessary. Yeah, okay. How about this one, particular solution? Yeah, that's when the third computation, yeah, this one, the third one, would have come into play. Simplify, and then you end up with 2 cosine of t. So yes, it works out. Of course, you can do all this by brute force computation, but it's tedious, too tedious. Now, prove that c1y1, c2y2 plus yp of t satisfies the same homogeneous equation. And let's see, I want to leave this proof to you. Let's see. No, I'm not going to show you. It's available in my notebook, but I'm going to leave this to you. Now, solve this initial value problem. Okay, let's do that. We got the solution here, c1y1 plus c2y2 plus yp, where y1, y2, and yp are like this. And then we have one equation, y of pi is equal to 0. Second equation, y prime of pi is equal to -1, with 2 unknowns, c1 and c2. 2 equations are 2 unknowns, we can solve it, yes. But then again, how tedious will it turn out to be? Yes, it will turn out to be really bad. You can use Mathematica to do that. Here I use a bit more advanced program here. Clear the variables and define y as, instead of c1 and c2, I use a, b, a times cosine of t over t, b times sine of t over t plus sine of t, yeah, a y1, b y2 plus yp, and then set up a system of linear equation. Y of pi is 1, y prime of pi is -1, and solve. I'm supposed to get a is negative pi and b is -1, and we have the final solution there. And as for the traditional method, oh boy, it goes kind of like this. Here, plug in y of pi is equal to 1. Okay, plug in pi, we get that. In this expression, plug in pi, we get this. And sine of pi is 0, so that drops out. Sine of pi is 0, that drops out. And cosine of pi is -1, so we get this expression. So in the end, what do you get? C1 is equal to -pi. That wasn't too bad. Not bad at all. The other requires some unpleasant derivative computation because, let's see, this one, you have to take the derivative using the quotient rule here, quotient rule there. And then you got some expression of the derivative, y prime of t, and plug in pi, and then set it equal to -1, and then find out c2, where c1 is known as -pi. Good luck with that. If you do it right, you're going to get -1. And consequently, we get the final solution like this. As for detailed computation, I'm going to leave those to you. Tedious but elementary.